Okay, let's get started. Hi, everyone. Welcome to RSWall webinar series, part 4, which is about strengthening internal stability by transitioning to the stiffness method for MSC walls. Today, I have with me Professor Richard Batters from our Queen's RMC. And it's a pleasure to have Dr. Batters here. He is a professor emeritus of civil engineering at RMC and part of Queen's RMC Geoengineering Center. And my name is Sina Javan-Koshtel. I'm the senior manager of the limit equilibrium team at Rock Science. So today, we will talk about RSWall, and the stiffness method in RSWall, which is one of the features that we added recently. And also, Richard is going to talk about the basics of a stiffness method. So let's get started. First, about Rock Science. Rock Science is the world leader in developing innovative 2D and 3D software for civil mining and geotechnical engineering. We have the experience of more than 25 years, and now we have more than 80 people in our main office in Toronto, with more than 10,000 people around the world using our products. We have 20 products for different applications: soil, rock, civil, and mining, and geological engineering. And we added a new program called RSWall, which is a new version of a deep soil program. And also RSWall is one of our newest programs as well, that it was released on March 2025. This is the ecosystem of Rock Science. Basically, how the programs that we develop, they integrate with each other. And we can see that, for example, slide 2 is integrated with RSWall, RSlog, RSFile, RS2, and slide 3. So since all these programs are developed in-house, we can easily integrate them. In today's webinar, I'm going to talk about 2 different programs, RSWall and Slide. Mostly the focus is on RSWall, and we will show you how different features in RSWall work. So about the RSWall, it's a quick video about different features. We have different wall types: MSC wall, gravity, cantilever, Gabion, abutment, block wall, and wraparound walls. So different types of walls that we have in RSWall. We have 7 different design standards: AASHTO, FHWA, NCMA, Australian, British Standard, and Eurocode, that you can pick the project settings. We have different modes of failure for different walls: external, internal, and reinforcement failure modes in the RSWall program, as you can see here. Also, to calculate active, passive, and tension reinforcement, different methods are available in the RSWall. This is a single segment MSC wall. Multi-segment walls are also possible to be created using the wizard, and this is how you create these multi-segment walls. You can create non-uniform and uniform block walls without reinforcement. This is a gravity wall. This is a cantilever wall. And Gabion walls that you can define the battered one as well. And this is an abutment that you can define constant loads for abutments as well. We have manufacturer libraries for blocks and geosynthetics in RSWall to make your models creation easier. You have different types of load: distributed, line load, and point loads in the RSWall program, and they can be vertical and horizontal. For geometry of back slope and front face, you can define them as infinite, broken, and user-defined, very flexible. And you can define uniform and non-uniform support configuration in RSWall. And you can show the results in different ways in the RSWall program. We have a detailed hand calculations. RSWall is not a black box, so every calculation can be found in the hand calculation part. It is seamlessly integrated with Slide 2 software. So you don't have to create another model in a Slide 2. It goes directly to Slide 2. And you can always export your profile and all these entities as a DXF and take it to other programs. So this is about RSWall. Today's discussion is about transitioning to the stiffness method for MSC walls that Professor Batters is an expert and who started this stiffness method. So we invited Dr. Batters to give us a presentation regarding this. So I'm going to pass the presentation to Professor Batters, and he's going to talk about it. Then I'll come back with the demo.
So again, thank you, Sina. Thank you, Rock Science, for inviting me to speak on a favorite topic. I just want to correct one thing. This development of the stiffness method was not me alone. It was there were other individuals, particularly Tony Allen at the Washington State Department of Transportation, and Yoshi Miyata in Japan. Here we are. I'm going to focus on the internal stability of MSC walls. And I'm going to assume that everybody out there knows what an MSC wall is and recognizes that one of the challenges with the design and analysis of MSC walls is keeping the reinforced soil zone coherent and stable. And in order to do that, one of the primary calculations, and indeed the key calculation, is to calculate what is the maximum tensile load in a reinforcement layer under operational or serviceability conditions. The limit states that we're concerned with are shown here, and they include a calculation for the nominal load, the maximum load in the reinforcement, tensile load in the reinforcement under operational conditions. And there's different ways of doing this. One method is the stiffness method. Another method is the simplified method. So the first thing we have to do is calculate what the loads are, and that is the focus of the stiffness method in this presentation. On the resistance side, we have to calculate the pullout capacity for each reinforcement layer, which is related to the length of the reinforcement that occurs between a hypothetical internal Rankine type failure surface and the free end. We have to know what is the allowable tensile capacity of each reinforcement layer. And in the stiffness method, we have to be able to calculate what is the maximum load to keep the strain in the reinforcement to an acceptable level, knowing that that if the strain in the reinforcement gets too high, that's an indicator that the soil has actually failed, and therefore the wall is not at a serviceability state, which is a primary assumption for the stiffness method. So the stiffness method is incorporated in load and resistance factor design codes in North America. So that includes AASHTO 2024 on the left-hand side, and in Canada in the Canadian Highway Bridge Design Code. And the essential description of the design limit state when you use LRFD is shown in this slide. This means that the nominal resistance term which you see here, is multiplied by a resistance factor, which is 1 or less, and the nominal load term is multiplied by a load factor, which is 1 or greater. And this equation has to be greater than 0 in order for the limit state to be satisfied. So returning then to how do we calculate the maximum tensile load? The essential concepts are shown here. Imagine we have a retaining wall facing here, and acting on the back of it is a distribution of lateral earth pressure. If we believe that that pressure was a Rankine type or a Coulomb type, then it's triangular in shape. And the job of each reinforcement layer is to carry a portion of that distribution. And that portion is calculated over a contributory area or spacing of each reinforcement layer. And we can calculate what this horizontal pressure is acting laterally by choosing an equivalent coefficient of earth pressure, knowing what the unit weight of the soil is, and knowing what the depth to the reinforcement layer is. Mm-hmm. And if one goes to AASHTO or the Canadian Highway Bridge Design Code and you decide to use the simplified method to calculate what the maximum load in the reinforcement is, you would use this equation here. And there is a chart which tells you that the equivalent lateral earth pressure coefficient is actually equal to the active earth pressure coefficient. This is for geosynthetic reinforcement materials, which essentially is saying that we're assuming with the simplified method that the soil is at an active state. If it's a relatively inextensible reinforcement material, we assume that the loads are larger, at least over the top half of the wall, due to the higher stiffness of the reinforcement. And therefore, you would pick a larger equivalent lateral earth pressure coefficient. So for geosynthetics, Kr is just equal to Ka. A question that myself and Tony Allen and Yoshi Miyata asked many years ago is, how accurate is this simplified method for the calculation of the maximum tensile load in the reinforcement under operational conditions? And to answer that question, we gathered, measured strain data from high-quality instrumented walls in the field, including, for example, geogrid walls. And we were able to gather about 90 measurements from about 96 instrumented layers. And this slide here shows an example of one of these walls. This is one of the Federal Highway Administration test walls that were built in the late 80s, early 90s by the FHWA to examine the performance and the accuracy of design methods. So you can see it's about a 6-meter high wall, and you can see on the right-hand side, the wall is about half built. You can see the reinforcement, the facing, and some extensometer measurement points, and even some slope inclinometer casings. And the data from this wall was particularly useful because the wall was actually designed so that when it was completed to the crest, according to current practice at that time, the factor of safety against overstressing of the reinforcement was 1. So then the wall was subsequently surcharged in order to encourage the wall to misbehave. In other words, to have a factor of safety less than 1 during surcharging. And what we found was that the strains in the reinforcement were still reasonably small. Even after surcharging, the strains were less than 2%. The walls did deform, and after surcharging, the deformations were larger, as we might expect. But this wall was never indicating that it was under any serious distress, and therefore showed us evidence that the current design method was very conservative. Another wall that was instrumented was the Rainier Avenue wrap face wall, which was built as a temporary support to a preload embankment that was used to pre-consolidate some compressible foundation soils at the location of a bridge overpass. You can see the cross section of the wall. It was actually highest wall of its type at the time that it was constructed, and again gave us the opportunity to strain gauge the layers. And even at the end of construction, the strains in the reinforcement were never greater than about 1%. Again, indicating that there seemed to be a large amount of excess capacity in the reinforcement for these types of MSE walls. Other structures were also instrumented. This is a prop panel wall that was constructed not far from where I am in Canada, Ontario. And we were able to place strain gauges on selected layers of reinforcement. And from those strain gauge readings during and at the end of construction, we were able to deduce what the actual tensile loads in the reinforcement were at the end of construction. And we gathered all of this data together, and we plotted the measured maximum tensile load in the reinforcement layers, as you can see on the vertical axis. And we plotted that against the predicted values using different design methods. And so when we used the simplified method and we looked at all of this data together, on average, we found that the measured tensile loads were about 3 times higher than what the simplified method predicted. In addition, there was a lot of scatter in the data. So the question was how to fix the predictions. And what we did is we took the simplified method as a starting point, because folks were familiar with this method. You've seen the equation here for this method. On the right-hand side, we've just expanded it a bit. And then we modified this equation by adding influence factors and a couple other factors in order to improve the prediction. And this slide just shows that some of the original terms have been modified by various collections of terms and new terms, as you can see here. I'm going to speak to those shortly. So we were a bit like structural engineers. If you ever looked at a reinforced concrete code, you'll see all of these empirical correction factors that have been introduced through experimental observation in order to improve the predictive capacity of these equations. So we basically did the same thing. And after this was done, we then plotted the measured loads against the predicted tensile loads using our new method, which we call the stiffness method. And what you can see, at least visually, is that there is better agreement between the measured and predicted results. And in fact, the agreement can also be shown through, quantitative statistical characteristics. And so the simplified method is now specified for the internal stability design of geosynthetic MSE walls in AASHTO 2024, and is also found in the Canadian Highway Bridge Design Code. for both extensible and inextensible reinforcement systems. And the signature feature of this method is that the creep-reduced tensile stiffness of the reinforcement is included explicitly in the calculation of reinforcement loads. And this is a paradigm shift from the simplified method, which was focused more on the strength of the soil and not the stiffness of the geosynthetic reinforcement. This slide here shows the influence of some of these parameters that we have introduced into the stiffness method equation. So the stiffness method equation is shown here. And the first parameter that we introduced was a parameter to better predict the distribution of reinforcement loads in these walls under operational conditions. And what we found from observation of full-scale walls in the field is the distribution was tended to be bilinear rather than linear with depth, as is predicted by the simplified method when you have simple geometry, same reinforcement type and uniform spacing. So this DT max corrected this distribution to follow a bilinear distribution where the reinforcement loads, once you get into the bottom half of the wall, tend to be uniform. The next term that I'm going to look at here is called the reinforcement stiffness factor. And this is the factor that accommodates the influence of the reinforcement stiffness on the development of tensile loads in the reinforcement. We don't have to look at details of these empirical factors, but focus more on this stiffness term, which is the secant stiffness. And this is the stiffness of the reinforcement from creep testing at a strain of 2% and a load duration of 1,000 hours. So this is an index stiffness. And what you see from this plot on the left-hand side is we still have the bilinear distribution of tensile load in the reinforcement layers. But as the stiffness of the reinforcement increases, the loads go up. And this may be understood by understanding that as the stiffness of an element increases in the soil structure problem, more load is attracted to that layer, and therefore the loads go up. So you may ask, well, how do we get this secant stiffness value, which occurs directly in our stiffness method? Well, the easiest way to get this data, or at least to understand how to get this data, is to look at constant load creep testing. So we can put a specimen of geogrid and hang a load on it and measure how this specimen will strain or creep with time. And from this data, we can construct secant stiffness versus strain curves. So the secant stiffness is simply the ratio of load divided by strain. As the strain increases for these polymeric materials, the stiffness actually goes down. So for design purposes, we have selected the secant stiffness that occurs at 2% strain and after the load has been in place for 1,000 hours. Now, so these values, like the 1,000 hour 2% strain, can be found in manufacturer literature, including NT-PEP reports. We simplified the selection of that stiffness value by plotting the measured secant stiffness values on the left-hand side, vertical axis, against the ultimate strength of the reinforcement. And what we found is that there is sensibly a linear relationship. So you can estimate what this secant stiffness value is by going to this chart and using this linear relationship. And a typical value of the ratio of secant stiffness to ultimate strength is about 5 for polymeric reinforcement materials. Now let's look at other influence factors in this formula. And here we see the facing stiffness factor. This factor recognizes that the facing can contribute to resisting the lateral earth pressures that exist in the reinforced soil mass. So for example, here is our reference case, and here we have a modular block wall. So it's a structural facing. And this corresponds to a facing stiffness factor of 0.8. And here you see the resulting bilinear tensile load distributions. If I then replace that facing with a wrap face, the facing stiffness factor increases from 0.8 to 1, and therefore the maximum loads in the reinforcement also increase. What you can see how is these curves have shifted to the right. So previously they were here, this is the block face, and here they're now higher because we don't have a rigid structural facing to help carry the loads. And this is something that cannot be accommodated by the simplified method. The simplified method ignores the potential contribution of the facing to reduce tensile loads in the reinforcement. Other factors include a facing batter factor. Essentially, what we have found by observation and integrated into the empirical adjustment of this simplified method equation is that if the facing itself is more than 10 degrees from the vertical into the soil or more, that batter tends to reduce the loads in the reinforcement. So that's actually included in this stiffness equation. We also can accommodate the influence of different stiffness reinforcement layers in a wall. You know, the case where you don't have all the layers of the same material. So that can also be accommodated in this stiffness method. Another factor is what we call the cohesion factor. What we observed is that if we have a granular soil that has a permanent, reliable, apparent cohesion, as you might measure in a direct shear box test, that cohesion is an indicator of a reduction in the tensile load in the reinforcement layers that we observed when we measured these loads for these types of walls. So here we have a case in which the dependable cohesion in the reinforcement is 5 kPa, and here we see the family of bilinear load distribution curves that we've seen before. If we have the same scenario and there's no cohesive component, or we choose to ignore it, then what happens is these curves shift to the right, because now more load has to be taken by the reinforcement. So here we have some apparent cohesion, and here we have no apparent cohesion. A unique feature of the stiffness method is what we call a soil failure limit state. The stiffness method was developed with the assumption that the soil was at a working stress or serviceability stress condition. It was not at limit equilibrium. It was not at a condition which was approaching failure as we understand it from conventional soil mechanics practice. And so in order for this stiffness method to be valid, the strains in the soil have to be kept below some critical threshold value. It's very difficult to measure strains in the soil directly. But what we found was we could use the strains in the reinforcement as an indicator of whether the soil was at a limiting state. And knowing what that value was, we could then design our wall so that the strain in the reinforcement did not get high enough to encourage failure in the reinforcement itself, which would be manifest as a continuous failure mechanism or slumping or cracking at the surface. So if we know what the maximum load in the reinforcement is, we know how to calculate that from our simplified method equation. We have a secant stiffness value that we've used in our calculations. And the ratio of those two values is simply the strain in the reinforcement under operational conditions. So we can calculate that value. And from observation of walls that have behaved badly and those that have behaved well, we found that if we kept the strains in the reinforcement less than about 3%, then we did not see indications of soil failure, cracking, slumping, continuous creep of the wall, this type of thing. So this became the strain, the critical strain that we must not exceed in order to satisfy this so-called soil failure limit state. And this is only applicable to the stiffness method and for the case in which we have extensible polymeric reinforcement. It doesn't apply to steel reinforcement. So here is our base case again. And for each curve or each layer, we know what the stiffness of the reinforcement is. We know what the load is. And therefore, for each layer, we can calculate what the maximum strain in the reinforcement is. And this example has been carefully crafted to illustrate that the maximum strains in the reinforcement are all less than 3%. And therefore, the soil failure limit state has not been exceeded. For many walls, this basic equation can be simplified. For example, if you don't have a surcharge, this term here disappears or becomes 1. If you have a vertical or near vertical wall, that is with a facing batter of 10 degrees or less, and a single reinforcement soil, reinforcement type, and no apparent cohesion, then the equation becomes much simpler, as you can see at the bottom. So it's not much more complicated than the simplified method equation. It's just got a few correction factors. The implementation of this method is a step-by-step procedure. And if you go to the LRFD code in the US, you can find all of these equations that I've spoken about, and you can walk through these equations for any trial design that you're interested in. The equations are quite simple. They're amenable to putting into a spreadsheet. And when we were developing the method, that's what we did. Just spreadsheeted these equations. You can also find guidance on how to use the stiffness method in the Federal Highway Administration GC 011. So this is a guidance manual, which is in sympathy with the AASHTO code, but includes a lot of details and advice to assist you to understand how to do these calculations. The same thing, the same method, as I mentioned, can be found in the Canadian Highway Bridge Design Code. And this code and commentary were issued just recently. And there's a link here to you can find this code on the web and purchase the same. Basically, the American code and the Canadian code should give you essentially the same MSC wall outcome. Okay, when we were developing the Canadian Highway Bridge Design Code, we were keeping our eyeballs on the American code in order that we don't have walls that are, practically different on both sides of the border. The advantages of the stiffness method, it's a robust empirical-based method based on observation. It has the advantage of being seamless across all MSC wall types, including polymeric and steel reinforced systems. In the past, there were two solitudes. There were the steel walls and there was the flexible polymeric walls. But the thing is, what really separates them is the stiffness of the reinforcement. Because the stiffness of the reinforcement is included explicitly in the stiffness method, this allows us to transit through both types of walls. It also includes polyester strap walls. These are fairly new systems. It gives accurate estimates of the magnitude and distribution of reinforcement loads under operational conditions. It includes a soil failure limit state, as I talked about before. It has been calibrated for LRFD codes, both in the States and in Canada. You can spreadsheet it, but more importantly, you can now use this method in software. In other words, RSWall, which Sina has spoken about and will speak again further. It's been used successfully for the design of walls, but it does have limitations. You only use it to calculate maximum reinforcement loads under operational conditions. You don't use it for limit states that are at incipient collapse or black swan events like earthquakes or tsunamis. It's limited to simple geometries, relatively small uniform surcharges, competent foundations, and soils that conform or meet the specifications for quality granular soils that you find in AASHTO and the Canadian codes. We're still working on making adjustments to this empirical method for the case of footing loads on top of MSC walls. That work is still going on. It doesn't consider larger failure mechanisms like compound stability or other global stability limit states. And like I said, it doesn't include earthquakes. So you may ask yourself, well, how do I consider these other compound or global stability limit states? Well, essentially, one can use, I hate to use the word conventional, but familiar limit equilibrium slope stability methods, but modified to include the contribution of reinforcement layers where they intersect critical failure mechanisms. And an example of this, of course, is our slide 2, which is in the suite of programs that Sina mentioned earlier that are available from Rock Science. Earthquakes, one of the things that we can do is we can add an additional dynamic tensile load to each reinforcement layer. And we just add that to the static loads that we calculate using the stiffness approach. And without getting into details, we assume that this is simply a uniform distribution. We can just add those loads to the each reinforcement layer. And we can also use these limit equilibrium slope stability models as, again, slide 2. So this is an alternative method of carrying out these types of calculations, which is actually more robust and gives you more flexibility to handle these types of load conditions. Our experience to date with the stiffness method is that the soil failure limit state usually controls. The requirement to keep the strains and the reinforcement to low critical values is most important, so that the soil is at a working stress condition. Connection failures may happen if the connection is very poor, but to be fair, the manufacturers of these systems have developed connections that are quite efficient, so not typically a problem. Pullout can occur, for example, in polymer strap walls at the top of the wall, because the coverage ratio, the reinforcement coverage ratio for these materials at the top of the wall is quite low. But you can increase the margins of safety against collapse, so failure due to pullout, often just by locally increasing the length of the straps at those locations. So there's a very quick overview of the stiffness method, and this method has been implemented within the RSWall software. And with that, I'll turn it over to Sina to explain the software.
So this is RSWall software. I'm gonna do a quick demo regarding the stiffness method, but I'll create a wall first with the simplified method, and then I'll do the stiffness method. So in RSWall, the welcome page, you can pick the type of wall that you want. So I just open an empty project. In the project settings, you can change the units, you can change the wall type, you can change the design standard, the AASHTO 2024. I'll talk about the new features. The AASHTO 2024 is the new one. I'll change it to 2020 for the sake of this example. We have different failure modes, external, internal, and reinforcement. I'm going to turn off the internal sliding and press toppling as well. For the methodology, which was basically the purpose of this webinar, for tension and reinforcement, we have simplified, coherent gravity, and the stiffness method. So I start with the simplified method. We look at the results, and then we go to the stiffness method. So I hit OK. Then in RSWall, you can define the wall units first. You can pick the modular block or wraparound walls. For this example, I'm going to pick a modular block. I'm going to create a single panel wall. For that, you just need to define a high block, which is like 6 meters, and then like other parameters for the depth and width of the wall, and shear capacity. This one is for the internal sliding of the block. So since we turn it off, it doesn't really matter. So I hit OK. Then we can go to the soil profile. By default, we have like 10 blocks. I'm going to change it to 1. So basically, it's a single block wall. And the height is 6 meters. It doesn't matter if you define a setback or a batter angle, because it's a single panel wall. Then if you want to create a single segment wall, you click on add wall. Otherwise, you use a wizard to create multi-segmental wall. For the sake of this example, I'll do the single segment wall, and the wall is created. Next would be to define a leveling pad for this wall. So I would go with 150 millimeters for the thickness, 0.9 for the width, and setback of 76. So once I hit OK, the leveling pad would be added to the wall. You can define the base strength, which has two parts. First part is for calculating bearing capacity. So based on soil properties, it means that we use Terzaghis method to calculate bearing capacity. You can do the user define and define your ultimate bearing capacity. This one is related to the contact of the wall with the soil. So this is the MSC wall, and we go with soil on soil. I did okay. Let me save this model somewhere. It's always a good practice to save models. So save it here. Next would be the soil section. We define the soil profile and properties in this section. For back slope, I'm gonna define a broken back slope. We can do user defined or infinite. It's gonna be 5.5 meters of slope run, 26.6 of slope angle. So when I hit OK, your back slope would change to this number. And for front face, I'm gonna have the 1 meters. And if you want to consider the passive resistance for permanent soil in front of your wall, you can turn this one on, and it will be applied here. Next would be to define soil properties. So we can have a backfill. So I'll keep the parameters. Then we will have reinforced.
Now,
and for the reinforced soil, I'm going to change the friction angle to 34 and soil structure friction, which is delta, to 30 and unit weight of 21. Third one would be foundation. For foundation, everything would be the same except I added 5 kPa of cohesion. I'm going to add another material for leveling pad. And the properties would be 24, 40, 27, and 10. So properties are defined. Then we will go and assign these properties. So you can just pick from the left menu and apply to the right side. So I picked a reinforced, foundation, and leveling pad. When you hit OK, everything is applied except the reinforcement part, because we haven't defined any reinforcement yet. Now we go to the loading and support tab. You can see that these tabs basically are the flow for your design. So we go to these tabs, we go to the loading and define the uniformly distributed load. So we start at 5.5 and the magnitude of 12 kPa and assign it to this segment. The load is added. Next would be to define reinforcement types. We do GeoGrid and we define 2 different reinforcement types. First one would be Husker 300, which has the ultimate capacity of 300. And for this one, we define the interface sliding friction angle of 12.5 and the connection of 32. Constant. And the next one would be again Husker manufacturing library, but this one we go with the 400, which has the ultimate capacity of 400. And for this soil interaction, we go with 15 and the connection of 35 and hit OK. Next, we will add a layout for our reinforcement layers. And here you can apply uniform and non-uniform. For the length, I'm going to go with 5.5. And you can uniformly apply the properties. I don't want the uniform properties. I want them to be different. I'll define 10 different reinforcement layers. And for the first 5 of them, we go with the stronger reinforcement, which is reinforcement 2. And for the placement, we go with the elevation, and it's going to be 0.2 and 0.6 for the spacing. So that's going to be the arrangement of my support. If I hit OK, you can see that the supports are being generated. So it's very simple process. Step by step, you can define your wall. So when I hit compute, you can see that the wall is, the results are being generated. Connection strength is governing factor of CDR. Capacity demand ratio is 1.06, which is a reasonable number. So this is for simple method. So if you want to take this model to slide, you can just with one click take the model to the slide program. The program asks you to save the model, and you can just compute. So click on compute, and you will see the results. So it's a very quick process. You can see the factor of safety of Bishop 1.6. So CDR of greater than 1 is acceptable. And this is a very simple method. Now, if we go to the presentation, Richard showed this paper in his presentation, Batterson Nachal in 2021. I want to borrow this figure from this paper and use the number, because if you want to do a stiffness method, you need this secant stiffness value. So if you saw in my reinforcement properties, they have the ultimate capacity of 300 and 400. So for that, we need to define like the secant stiffness if you want to do the stiffness method. So I'm going to go to the project setting, change the method to a stiffness method, and hit OK. Results will be removed. So we go to the support properties and change this secant stiffness method values. So if I go back to my presentation, we have 300 and 400. So basically for ultimate capacity of 300 and 400, we need the secant value, which is going to be, for 300 is going to be 2800, and for 400 is going to be 3500. So I go back to reinforcement 1, I'm going to change this one to 2800. And for reinforcement 2, I'm going to change it to 3500. So these are the new secant values that we picked from that chart. In future, we will add that chart to this RSWall program, that it would be easier for our users to pick the numbers for these secant values. Then hit OK and compute. So you can see that factor of safety, base sliding wasn't controlling for the simplified method. Connection in the second layer was controlling. And factor of safety, or CDR, was 1.06. Now it jumped up to 1.76. And I think it's a reasonable number, the difference between the stiffness method and the simplified method. You can always go to the report generator of RSWall and look at the hand calculations, as I mentioned. So if you go to the results, for example, a summary, it's going to give you all the CDRs, base sliding, overturning, bearing, and 4 CDRs for every layer based on different modes of failure. And every calculation is provided here with reference to the AASHTO standard. So this example was AASHTO, so every equation, every figure is based on AASHTO. So you can easily export this one to PDF and present it to your clients. So what's new in RSWall? We released a new version on Friday afternoon. So it's going to be RSWall version 2, 1002. You can download it now. It is available. You can try it. You can request for a trial. What we added was a couple of things. First was we added AASHTO 2024. Now in RSWall, we have ASD, allowable stress design for AASHTO and Eurocode as well. So it's just based on factor of safety and not LRFD. So it's a new addition to the program. We released a feature called tension map. Basically, you use a method in the slide to calculate maximum tension in each support layer using limit equilibrium, and then you can directly take it to the RSWall program and do the analysis for a target factor of safety. So that's a new feature added to slide 2 and RSWall. And the last but not the least, which is a game changer really in the field of MSC wall design, is called support designer. Basically, what you need to do is to define your default factor of safety. Then the software picks the parameters that you defined originally in the program. And you don't have to define any reinforcement layers. You just need to define your parameters. And the software generalizes a couple of designs for you. What it can be baseline design or optimized design. We use advanced optimization techniques to create optimized designs for you for your target factor of safety. So no trial and error anymore. Just give us your parameters and we give you the design. It's going to be a couple of articles and videos related to this feature. Keep in mind, if you already have a design, you can pass it to this tool as well, and it's going to optimize it for you. So it's not only it's a designer, it is optimizer as well. So give it a try. Let us know your thoughts about this, because this is something that a lot of people requested, and now you don't have to do anything. The software generates the design for you. Keep in mind, this feature considers the cost of reinforcement if you want as well. So cost per area, if you put it in the as an input here, the output is gonna consider this cost as well. So thanks everybody for attending the webinar, and let us know if you need anything from us.